Yep. We'll be live now. So, hello, everyone. Good evening. All of you who have been waiting for this session, people were giving us some memes and other stuff about the JWTS, the James Webb Telescope. People were asking about the Hubble Space Telescope. In the last week, we had a good discussion on Kalam Labs YouTube channel in which we were talking about how things can change once we have better resolution, better powerful machines, and better telescopes like the JWTS. And all the people of India who have joined us from abroad as well and other places, the session has begun. And yeah, hello. So there's one convention which we always follow at Kalam Labs, and I think we should basically follow it today as well. So whenever I ask you that how are you, the answer to that question is we are curious, right? So all the people who have joined now and they want to meet Matthew sir and to discuss about the JWTS Space Telescope, write down in the chat section, we love science. That is the thing by which we can basically initiate a session and we will be talking forward and like we'll be meeting Matthew sir with it. Okay. So everyone in the chat, please write down we love science, because this is the only way by which any session on Kalam Labs is open, right? So we love science, we are curious, we are curious. Correct. Okay. So, hi Selvin, hi Ariman, hi Ami, and Neha, Tejas, Priya, everyone who are watching us live. We are curious, right? That is the only thing, because the answer to the question is, how are you? Okay. So, nice. So I think it's nearly 5 p.m. Only 1 minute is remaining. So all of you who have certain friends in the school, you can call them up. And then we can come to this live streaming. And Matthew sir can also come here. Yes, we love science. We love science in the chat. People are writing in we love science. That's great. Wow. So a lot of enthusiasm for this session. I can truly understand like all the messages which were coming so far about the JWTS, the James Webb Telescope, what it is, who is James Webb, what is being designed over NASA, what is Goddard Flight Center, they are designing it, what is the kind of this telescope, all these little curious questions which are coming. The time has come when we'll be discussing for 1 hour with Matthew sir, who's joining us live in 1 minute. And the other thing is that after 40 minutes of the session, we will be giving out the opportunity to you to basically ask question yourself. Okay. So we have basically given out option for sending us video question answers, like video questions which you can ask in the session directly. And if not, you have not sent us the video, then don't worry, just write your question in the chat or in the comment box, and we will definitely reach out to you. And all that will happen basically 40 minutes afterwards. Okay. So I think it's 6 p.m. It's 6 p.m. And hello, Matthew, sir. Thank you for coming into this session with us. All the people who are there, they are basically saying hi to you. More than 800 people who are watching us live right now. They are welcoming you to the channel, sir.
Well, good evening, everyone, and thank you very much for tuning in to learn about the James Webb Space Telescope.
Yep. So, like, we all have heard about Hubble Space Telescope and other stuff. We have been like in every encyclopedia about space, Hubble Space Telescope was always the page which used to come at the first and the primary. So like at the first page of any encyclopedia of space, we can spot Hubble Space Telescope. And I read a fact about it that I don't know how correct it is, but if Hubble Space Telescope is a magnifying glass, then JWTS will be a microscope to the level. Like if we take the scales, if we consider the scales. So what are your thoughts on that? Like what is JWTS and other things?
Well, we'll be talking about how JWST differs from the Hubble Space Telescope. Yes. And what kind of science it will do that the Hubble cannot do.
Yes, exactly, sir. So everyone, Matthew sir has joined us live, and all the people, hi sir. That's a great response. That's a very good response, which we always give to our live speakers. So Matthew sir is basically hailing from Goddard Flight Center, USA, and he has been working as a project scientist at the Goddard Flight Center in the JWTS, James Webb Telescope section. He has been working there since more than 25 years, I think, and he is one of the most celebrated and reputed scientists at NASA. So over to you and all the eager, curious people who are watching us. They all are all ears to you.
Okay, great. And are my charts visible right now?
Not yet, sir. You can share the screen.
Okay, let me do that.
Yeah.
How about now?
Yeah, it's totally visible, sir.
Okay, great. All right. Well, thank you everyone for tuning in to learn about the JWST telescope that will be launching in October. Now, traveling back in time is the stuff of science fiction, but looking back in time is science fact. Looking back in time is something that we can actually do. And it's made possible by the finite speed of light. If you look at someone who's in the room with you right now, you're not seeing them as they really are. You're seeing them as they were a few nanoseconds ago, a few billionths of a second ago. Now, a nanosecond is a really small amount of time, so we don't perceive that delay. But as we look at objects that are farther and farther away from us, this delay becomes more significant. For example, if we had a magic switch that could turn off the sun, and we turned off the sun, we would not know that anything happened for 500 seconds. That's because it takes 500 seconds for light to travel from the sun to the earth. So when we look at the sun, we're seeing it not as it is, but rather as it was 500 seconds ago. Similarly, when we look at the nearest star, we're seeing it as it was 4 years ago. And as we look at the center of our galaxy, we see it as it was 25,000 years ago. And so it goes. As we look at objects farther and farther away from us in space, we are literally looking back in time. And this is what astronomers use telescopes for primarily, to look back in time. Now, the JWST mission was conceived in the late 1990s as a mission to relate this famous image of the oldest light in the universe. This image was taken by NASA's COBE satellite. A Nobel Prize was actually awarded for this image, and it shows us what the universe looked like when the universe was only 300,000 years old. At the moment the universe became transparent and light could escape after the Big Bang, this is what it looked like. At about the same time, the Hubble Space Telescope had taken the deepest image that it's capable of taking. It had looked as far back in time as the Hubble is capable of doing, to a point in the history of the universe where the universe is about 1 billion years old. So we were able to see this epoch and this epoch in the evolution of the universe. But between those epochs, there is a mysterious epoch that has never been observed called the cosmic dark zone. And the reason that the cosmic dark zone has never been observed is that we've never had the right type of telescope in space to observe it. But it's a very important epoch. It's of great scientific interest because it is at this point in the evolution of the universe that the first stars in galaxies formed. And so the JWST mission was conceived as a mission to connect the dots, if you will, between this famous image and this famous image shown in an evolutionary context on this cartoon. It is the primary goal of the JWST is to observe the birth of the first stars and galaxies after the Big Bang. Now, when the Hubble Space Telescope takes the deepest image that it can take, it does this by staring at a single spot in the sky for a long, long, long time, leaving the camera shutter open, if you will, to see the very faintest objects that the telescope is capable of seeing. And when it does that, one sees an image like this, and this image still contains many faint red galaxies. We have not seen the beginning. There are still many, many galaxies in the image. Now, when the JWST flies, it will repeat this experiment. Again, it will stare at a single spot in the sky for a long, long, long time. But unlike the Hubble, the JWST should be able to see far enough back in time to see the epoch of galaxy formation, to see the formation of the first stars and galaxies. So when the JWST takes its deepest image, it should see all there is to see. Now, when we say that the JWST will see the first galaxies, we don't mean that you will pick up a copy of the newspaper and see a picture of the first galaxy. What we mean is that we will measure the star formation rate in the universe as a function of look back time, as a function of how far back in time we're looking. And this is what we know today, these data points. And with JWST, we'll extend this plot way to the right. We will see a precipitous drop off, and that will be the formation epoch. And with that new data, we will be able to test various models, theoretical models, of how the universe evolves to determine which models are correct, which models best fit the data. Now, in addition to seeing the first stars and galaxies, we want to understand how the universe has evolved from that point. What you see running here is a supercomputer simulation of the evolution of the universe. And this shows what we know today about the structure of the universe. All these little blue dots are clusters of galaxies and individual galaxies. And the matter in the universe is actually distributed in space the way you see it here. It's distributed in a spider web type arrangement called the cosmic web. And it's of great interest to understand how this structure formed and evolved. And the web will help us understand that. When you look at pictures of galaxies in your textbooks and posters in your classroom, you'll see that they have very symmetric, regular shapes. Some of them have spiral arms, some of them have bulges and bars, but they're very symmetric shapes or morphologies, as we say. But when we look at galaxies far back in time, if we look at the faintest galaxies that were visible in that Hubble Space Telescope image and zoom in on them, they don't have those shapes. They look very irregular and very asymmetric. And so as we look back in time, the galaxies go from looking like this to looking very beat up and funny like this. And so this is a great scientific interest, and this is something that the web will help us understand as we look back in time to see how these galaxies evolve. There are many examples of these irregular shaped galaxies that we see nearby. And this is a theoretical model of two galaxies colliding. And with models like this, we can actually reproduce those shapes or morphologies. And so we believe that the reason that the galaxies look different earlier in the history of the universe is that these galaxy collisions were more common then, and that galaxy collisions is the root cause of those morphologies. But JWST will allow us to see what's true. Now, you've all heard the statement that the universe is expanding. What do we mean about the universe expanding? In this cartoon, we have a lump of raisin bread dough. And if we set the dough out to rise, as shown here, imagine that you are sitting on one of the raisins. What would you see? You would see all the other raisins moving away from you, even though you are not at the center of the expansion. No matter what raisin you sat on, all the other raisins would be moving away from you. This is an analogy for what we mean by spaces expanding. We don't mean that the galaxies are flying through space, but rather that the space itself is expanding, just like the raisin bread dough is expanding. Now, when we look at distant galaxies, the light emitted by the distant galaxies is emitted in the ultraviolet part of the spectrum. But as the light travels to us through that expanding space, the wavelength is stretched from the ultraviolet into the infrared. So to see those early galaxies, those primeval galaxies, to see them today, we need to observe in the infrared part of the spectrum. So what do we mean by that? Light comes in a spectrum of wavelengths, an infinite spectrum, from infinitely short to infinitely long. And our eyes are only visible to a small piece of this spectrum, a piece for which the Earth's atmosphere is transparent. So our eyes have evolved to match this transparent window in the Earth's atmosphere. But there's much more light to see that our eyes cannot see. In longer wavelength than visible light, we have the infrared part of the spectrum. Our eyes can't see the infrared, but our skin can feel it. If you hold your hands near a stove burner, your hands can feel the heat from the burner, even though the burner might not be glowing at all. It might just appear black. Your skin is sensing the infrared light emitted by the stove burner. Similarly, shorter wavelength than visible light, we have the ultraviolet part of the spectrum. Again, our eyes can't see the ultraviolet light, but this light can burn our skin. So if you spend too much time in the sun at the beach, you can get a sunburn. That's from the ultraviolet light. The Hubble Space Telescope is designed to observe in the visible and ultraviolet, so it cannot see the light from the first galaxies. The Hubble Space Telescope is designed to observe the red part of the visible and the infrared part of the spectrum so that it can see the light from the first galaxies. Now, that infrared capability to see the first galaxies is also important for doing lots of other science that the Webb telescope will do. The spaces between the stars in our own galaxy is not an empty vacuum. The so-called interstellar space is filled with clouds of gas and dust. This is a famous Hubble Space Telescope image of one of these giant clouds of dusty molecular gas. It's called the Eagle Nebula. And these pillars are clouds of gas. The pillars are opaque because of the dust that they contain. But if we look at that same field in the infrared, the longer wavelength infrared light can see through the dust. So this is very important. We want to understand with JWST the details of how stars form in our own galaxy and others. We know the basics of star formation. These giant clouds of molecular gas collapse on themselves by self-gravity. And as they collapse onto themselves, the pressure inside the clouds gets very high. And as the pressure gets high, the gas gets very hot. So it's much like filling a bicycle tire at a gas station. When you fill the tire to a high pressure, the tire gets warm. The same thing happens in these molecular clouds in space, only the temperature gets very warm. It gets hot enough to the point where nuclear fusion can occur, and then stars are born and can shine. So we know the basics of star formation, but we don't know the details. And JWST will allow us to study this phenomena in great detail. We know that when stars are formed, there is typically a disk of debris that's left over from the star formation that surrounds the newly formed star. And these disks of debris are very interesting because they are the places that planetary systems form. And so to understand how planets form, we need to study these disks of debris, and JWST will do that. This is an artist's conception of the debris disk around our own star, the sun, alongside a map of where that debris actually exists. These are the so-called Kuiper belt objects or trans-Newtonian objects that exist in the outer reaches of our solar system. These big rocks and clumps of rocky ice are of great scientific interest because they are primordial material left over from the formation of our own solar system. And their nature is somewhat a mystery. We visited the first Kuiper belt object with a space probe called the New Horizons mission just a few years ago in 2014. The New Horizons mission was a mission to the planet Pluto, or the dwarf planet Pluto. And when we finished flying by Pluto, we sent the New Horizons mission to a Kuiper belt object. And we got the first close-up picture of a Kuiper belt object. And this is what we saw. The object turned out to be two smaller objects that were fused together. And we can model the formation of this two-body unit as a low-velocity collision in which the objects stick together. And this is of great interest to understanding how planets can form by agglomeration of smaller bodies. And we've put special tracking into the JWST to allow it to observe objects like this. Now, with that special tracking that we put into the JWST, we'll also be able to observe the planets of our own solar system and comets and asteroids. JWST can observe the outer planets, and so it can observe the outer planets, Jupiter, Saturn, Uranus, and Neptune. They're shown in scale against the sun here, and in comparison to the Earth here. So these planets are very much bigger than the Earth. JWST will be able to observe Jupiter. One of the things we'll do on Jupiter is to study the Great Red Spot. The Great Red Spot is a giant storm on Jupiter that's been raging for more than 400 years. But today we see it as suddenly shrinking. And JWST will hopefully help us understand why it's shrinking and also why it's red. We still don't know why the Great Red Spot is red. JWST will be able to observe Saturn, and we'll be able to see moons of Saturn that are too faint to see, too faint to have been discovered with flyby spacecraft that have visited Saturn. The moons of Jupiter and Saturn, Europa and Enceladus in particular, are very fascinating objects. Most of the liquid water in the solar system is actually not on the Earth. It is on Europa and Enceladus. These moons of Jupiter contain vast oceans enclosed by a crust of ice, and these oceans could contain life. The water and water vapor on Europa and Enceladus erupts through the icy crust to form geysers of water and water vapor that the JWST can observe. JWST will observe Uranus and Neptune. Neptune will study why Neptune has these great dark spots but Uranus doesn't. And we'll also study why the surface temperature, the upper atmosphere of Uranus is warmer than Neptune is warmer than Uranus, even though it's farther from the sun. So studying the planets will be an important part of the JWST mission. Now, today we know that all stars have planets. And as a consequence of having learned that, we now know that there are billions of habitable worlds in our solar system. That doesn't mean they're inhabited, but we know that there are billions of worlds where life can exist. And so today, searching for extraterrestrial life is not the stuff of science fiction. It is a major science objective of NASA. And we've learned how to search for life on these exoplanets, planets that are orbiting stars other than our sun. We've learned how to search for life on them by studying their atmospheres. And JWST is very much designed to do that. We do it by a process called spectroscopy, in which we use an instrument to spread light out to its component colors so that we can see emission from individual atoms and molecules in the atmosphere of the planet. Here we have the spectra of the Earth, Mars, and Venus. And one can see all these little bumps and wiggles in the spectra. So this wiggly line is a plot of brightness versus wavelength. And you can see all these bumps and wiggles are due to emission and absorption by individual atoms and molecules in the atmosphere of the Earth. If the Earth had no atmosphere, this spectrum would just be a flat line. And we have learned how to identify which atom and which molecule is producing every little bump and wiggle. So we will be observing the atmospheres of exoplanets to search for chemical species that would only be expected in the presence of life. They're called biomarkers. And by observing enough biomarkers in an exoplanet's atmosphere, one can make the case that life exists there. We will be focusing on planets that contain water. Why do we care about planets that contain water? It's not because alien life might get thirsty and need something to drink, but rather in order for the organic chemistry of life to occur on a planetary scale, one needs to have a liquid solvent that exists on a planetary scale, and water is what we're most familiar with. And JWST can detect water on an exoplanet that is just a few times the size of the Earth. So this should be a very exciting aspect of the JWST mission. Now, in the late 1990s, when we first put pencil to paper on what type of observatory we had to build to do all that science, we realized that we had some big problems that almost stopped the project dead in its tracks. First, we realized that we needed 7 times the light gathering capacity of the Hubble Space Telescope. That's because those primeval galaxies are really, really faint. So we needed a much bigger mirror to collect the light from those faint objects. And as I mentioned, we needed to build a telescope that could see in the infrared part of the spectrum. And to observe in the infrared part of the spectrum, we have to make the telescope very, very cold. This is because everything above absolute zero emits infrared light. So if you had infrared goggles on right now, you would see the walls, the floor of the room you're in glowing. You would see your body glowing in the infrared. And if we didn't make the telescope very cold, it would be blinded by its own infrared emission. And so we found that we needed a mirror with a diameter that was bigger than the biggest rocket. And we needed to make the telescope really, really cold, minus 200 degrees Celsius. And there is no mechanical refrigerator that can cool something as big as the JWST to such a low temperature. So we had to solve those problems in order to make the JWST mission possible. So let's first talk about how we solved the thermal problem, the problem of how to cool it. We determined that we would not put the JWST in orbit about the Earth, the way the Hubble Space Telescope is. Rather, we would put it in orbit around a spot in space called the second Lagrange point of the Earth-Sun system. That's a mouthful, but it's a point that we call L2, and it's about 1.5 million kilometers in the anti-sun direction from the Earth. It's right here. And one of the things that's special about that spot that makes it ideal for getting the JWST telescope cold is that one can see that all the sources of heat on the JWST, the sun, the Earth, and the moon, always lie in the same direction as seen by an object at the L2 point. So we realized that if we deployed a giant sun shield that was big enough so that the JWST could always live in the shadow of the sun shield, it would cool by radiation to the cold darkness of space to the desired temperature. So that's what we did. We designed a giant sun shield, and we were able to do it so that the JWST could always live in the shadow of the sun shield, and yet it can still observe the whole sky. So it works like this. We designed a sun shield big enough so that the JWST could tilt 5 degrees toward the sun. We're still in the shadow. We can observe 45 degrees away from the sun. We're still in the shadow. So now we have observed an arc on the sky that's 50 degrees long. And you can see that if we rotate the JWST about the Earth-Sun line, about this axis, that doesn't spoil our shadow situation at all. So now this arc turns into an annulus that covers 35% of the sky. So at any instant in time, the JWST can observe 35% of the sky and still be in the shadow. And now as the Earth and the L2 point orbit the sun, we're rotating about this axis. And so every 6 months, this annulus covers the whole sky. So every 6 months, the JWST can observe any spot in the sky and still be in the shadow. It's very important that it always be in the shadow, because once the JWST is cold, if the sun shines on it, the telescope could break. Okay, now I said that we would put JWST at the L2 point. In reality, we're going to put it in a little orbit about the L2 point. And this is because we have to stay outside the shadow of the Earth. This is because we are generating electricity with solar rays. And so we always have to have those solar rays exposed to sunlight. And this little orbit about the L2 point is an unstable orbit that has to be maintained by station-keeping thrusters. And the propellant for those thrusters is the expendable supply that will limit the life of the JWST to about 10 years. So after that propellant is used up, the mission will be over. The JWST will just fall out of this orbit into some general sun-centered orbit, but it will no longer be able to work as a telescope. Another thing that makes the L2 point ideal for our mission is that, as many of you know, when you place an object in space that is farther from the sun than the Earth, it orbits the sun with a longer period than the Earth. It takes a longer than 1 year to complete an orbit about the sun. But the L2 point is an exception to that. The L2 point orbits exactly with the same period as the Earth. So the telecommunications range between the JWST and the Earth will remain constant throughout the whole 10-year mission. And that's important for us to get the data back to Earth with radio transmissions. Okay, So we needed that mirror that was bigger in diameter than the biggest rocket. So how did we solve that problem? We solved it by adopting something called a segmented mirror architecture. The JWST mirror is composed of 18 hexagonal segments that can be adjusted so that they play together as if they were all pieces of a single mirror. And this allows us to fold the JWST up inside a 5-meter diameter rocket fairing. And we will launch the JWST on a French rocket called the Ariane 5 that will be launched from French Guiana. French Guiana is on the east coast of South America. And we will launch it there on the Ariane 5, and it will fly directly to the L2 point. It will not orbit the sun even once. And the JWST is about 6.5 metric tons. And I will show you how, in the next slide, how this unfolding occurs. But the origami that you will see in the next animation involves 40 deployable structures and 178 release mechanisms, every single one of which has to work perfectly. This is because the astronauts cannot go to the Sun-Earth L2 point. So if something doesn't work, the astronauts can't fix it as they did with the Hubble. The first thing that happens after we come out of the rocket is the solar rays deploy so that we can become power positive. We're operating on batteries up to that point. Here you see the high gain antenna deploy so that we can begin communicating with the JWST. And these various maneuvers that you see are designed to navigate us to the Sun-Earth L2 point. And these pallet structures that you see unfolding now contain that giant sunshade. You see a deployed mast here extend to provide thermal separation between what is going to be a very cold telescope and what must remain a warm spacecraft. And now these telescoping booms are pulling that sunshade out of the pallet structure. And then the sunshade will separate into its 5 layers that's needed to give it the thermal properties it needs. A trim tab deploys to help us trim what is now a giant solar sail. And in a moment, you will see the telescope itself begin to unfold. This is the secondary mirror of the telescope unfolding. And now the wings of the primary mirror unfold much like a round drop leaf kitchen table. And there you have it. That's how the unfolding works. And this will take place over the first 3 weeks of flight or so. Now, the JWST mirror is not made of glass. It's made of a material called beryllium. And this is because this mirror is going to operate very, very cold, about 50 degrees above absolute zero. And we needed a material that would have the right thermal and mechanical properties to operate at that low temperature. And beryllium was a good choice. The beryllium is mined and refined in a powder form, and then we press it under tremendous heat and pressure to create a big block of material called a billet. And then after going through all the trouble of doing that, we machine most of it away to create the lightest possible mirror segment that we can. This is the back and the front of a JWST mirror segment. And weight is crucial to anything that flies, whether it's a spacecraft or an aircraft. Minimizing weight is key. And the JWST segments are about 6 times lighter than per unit area than the Hubble Space Telescope mirror. So this is a new state of art for making lightweight telescope mirrors for space. Now, we have to polish these mirrors. And how do we polish mirrors? We polish mirrors by rubbing on them with gritty stuff until they get smooth and shiny enough. And that's a room temperature operation. But as we cool these mirrors from room temperature to, minus 200 Celsius, the mirror will change shape. And so we have to polish in the wrong shape at room temperature so that we get the right shape at the operating temperature. And to do that, we do it with the magic of computer modeling, but computer modeling is not perfect. And so we had to follow an iterative process whereby we polish the mirrors partway, and then we put them in a special space simulation chamber at Marshall Space Flight Center near Huntsville, Alabama. And this is a chamber, a giant tank designed to simulate the cold darkness of space. It's a big tank that is lined by shrouds that are cooled with liquid nitrogen and liquid helium to create the conditions that the JWST will operate in. And then we're able to observe those mirrors with special optics test equipment that tells us whether our modeling is correct. And we would then adjust the modeling so that we could get the perfect shape we want based on the wrong shape that we polish in at room temperature. So it took us many, many years to make these 18 segments, but we did it successfully, and all that work is behind us now. Now, in addition to making the mirrors, we had to make a structure that would hold the mirrors in place. And the requirements on this structure were very difficult. The structure had to be strong enough to withstand the inertial loads of the rocket flight needed to, get off the Earth. And at the same time, it had to hold all those mirror segments in exactly the right position to a unit of length that's equal to about the wavelength of light. So less than half a micron accuracy. And it had to do that over about 300 degrees of temperature change. So we had to invent a composite material that would have these properties to build this structure out of. And the structure contains more than 3,000 piece parts. But as you can see, all that was accomplished successfully. And so this is what the structure looks like before we put the mirrors onto it. This is a walkout deployment test of that secondary mirror structure that you saw in the animation. And this is just an example of some of the kinds of testing that we have to do to build things like this. Engineering is an empirical science. And so we have to do experiments like this to understand how our designs behave and to ensure that they will in fact work. This is a robotic pick and place machine that was used to place the JWST mirror segments on that backplane structure. And these are the actual flight mirrors. They look black because they have covers on them to keep them clean. And this robotic arm has a very high precision tool on the end of it that is helping the technicians get each mirror segment in exactly the right position to build up the primary mirror. You get the idea. This is an example of how we handle the actual flight telescope. This is in a clean room at Goddard Space Flight Center. And this is the actual telescope. This back wall here that looks like it's made of funny brown tiles, that whole wall is made of special filters called HEPA filters, so that this whole giant clean room is cleaner than a medical operating room. All right, let's talk about that sun shield. The JWST sun shield is literally the size of a tennis court. It's 73 by 40 feet. And it has 5 layers that give it an SPF of 1,000,000. So if you had this sun shield on the beach, you would be very well protected. It's made of a heat resistant material called Kapton. and the sun-facing side of it is coated with silicon. So it actually is pink in reality. All the other layers are coated with aluminum. And you'll notice that the sunshade is not flat. It has a curved shape. And those of you who sew know that you can't make a curved shape out of flat cloth without making a quilt. And so each layer of this sunshade consists of a quilt of about 50 pieces. And the seams that hold those 50 pieces together are about 7,000 inches of seaming. And here we're not using needle and thread to make the quilt, but rather thermal spot welds. And so this sunshade, the technology to build the sunshade, was also something that we had to invent to make the JWST possible. This is a walkout deployment test of how we fold up the sunshade in those pallet structures that you saw unfold in the animation. These plastic tables are providing gravity offloading. So those tables aren't there in space, but you can see the telescoping booms that you saw in the animation pulling the sunshade out of the pallet structure. If you look closely, you can also see the quilting. And you'll notice there's a person that appears in the middle here that gives you a sense of scale of how big this sunshade actually is. And this is one of the most important items in the JWST flight system. Without the sunshade, the JWST can't work properly as an infrared telescope. Okay, let's talk about the science instruments. The telescope collects the light from those faint objects that we'll be observing and sends it to the science instruments that will record the light, digitize it, and turn it into ones and zeros so that we could radio the data back to Earth. This is the main near-infrared camera of the JWST. This is the instrument that will observe those first galaxies and stars to form after the Big Bang. This is the main near-infrared spectrometer on the JWST. This is an instrument that will spread the light out into its component colors so we could see the emission from individual atoms and molecules. It is a very special instrument in that it's designed to observe 100 objects at a time and still keep their spectra separate from each other. And that's because the objects we're observing are very faint. So if we had to observe them one at a time, it would take too long to observe a sufficient number within the 10-year mission life of the JWST. The mid-infrared instrument, observes the longest wavelength light, will give humanity its first high-definition view of the infrared universe. For the very first time, we will be able to see the infrared universe with the same detail as we see in the Hubble Space Telescope images of the optical light universe. And then finally, we have the fine guidance sensor, which helps us point the JWST at the objects of interest. The fine guidance sensor can sense pointing to about 1/1,000,000th of a degree, or 3 milliarc seconds. And this instrument has spectrometers in it designed specifically to study those exoplanet atmospheres and search for life on other planets. Now, after we integrated or attached those science instruments to the telescope, we put that assembly into a special shipping container that's designed to preserve it in a special clean atmosphere that's needed to keep it qualified to fly in space. And we put that into a C-5 transport aircraft. It fits in there just barely. And we flew it from Andrews Air Force Base near Washington, D.C. to Johnson Space Flight Center near Houston, Texas, in order to conduct what is known as an end-to-end optical test in the largest space simulator in the world. It's called Chamber A at Johnson Space Flight Center. And this is a giant simulation chamber that was built for the Apollo program. This is a view looking in the door of that chamber, and you can see the Apollo command module here that was tested in that chamber. We had to resurrect this chamber out of storage to bring it back to life and use it to test the JWST. And in our case, we rolled the JWST in on rails into that chamber to observe special optics test equipment in the top of the chamber. So this is a giant vacuum tank with walls that are cooled by liquid nitrogen and liquid helium to simulate the environment that the JWST will see at the Sun-Earth L2 point. And we shine light through the whole system in order to make sure it's working. That's a test that we did not do on the Hubble Space Telescope program, with consequences that some of you were aware of. The Hubble didn't work when we first turned it on. The astronauts had to go fix it. In our case, the astronauts cannot go to the L2 point. So we decided not to skip that test on the JWST program, even though it's a very expensive, difficult test. And it's a good thing we didn't, because we did find some problems when we did this test. But that work is all behind us now. So then we went back onto the aircraft, and we flew from Houston, Texas to Los Angeles, California, where our contractor, Northrop Grumman Aerospace Systems, would attach the spacecraft and that giant sun shield. Okay, so let's take a look at that. This is occurring in a giant clean room at Northrop Grumman in Los Angeles. Now, having completed the assembly, we're not done yet. We had to fold it up and put it into an acoustic test chamber to blast it with loudspeakers that simulate the sound that it will experience in the rocket flight. And then we had to put it in a vibration chamber to simulate the vibration that it'll experience in the rocket flight. And then we had to completely test it and make sure it still worked. All that work is behind us now, and we're now in the final stages of getting the JWST ready to send to the launch site. Now, having put on the spacecraft and the sun shield, it's now too big and heavy to fly on the C-5 aircraft. So instead, we will roll this container onto a roll-on, roll-off transport ship that will ship out of Port of Los Angeles and travel through the Panama Canal to French Guiana, where we can begin the final launch processing, the job of putting the JWST into the rocket and getting ready to launch it in October. So this sea journey will begin this summer.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures, temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sun shield ever flown, a 5-layer, tennis court-sized sun shield that blocks heat from the sun, Earth, and Moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge.
JWST will be launching in October. You can follow the action at NASA Web, #JWST, and I'll be happy to answer your questions.
Yep. That was an amazing presentation, sir. Like the last scene of the videos, and it's your telescope. I think all the people and all the kids who were in the chat, they were all saying the same thing. It's our telescope. It's our telescope. So it was a really amazing session, sir. And now there are a lot of questions which were coming up. So can we begin with the Q&A session, sir? Now. Sure. So, sir, like there are many people who were talking about the hexagon shape which was present at the JWTS. So why it is only hexagon? Is it something which is related to the hexagon in the honeybees or the special features of the shape itself?
Well, we considered all different shapes, but the hexagon shape worked best for us. It allows all the segments to be identical and fit together with minimum gaps. And it was the simplest solution to segmenting the mirror.
Okay. Great. So like it's based on a simulation when we tested which shape can work best. The hexagon was the shape. Great. So now we have some video questions. So all the people who are in the chat, you can start typing your questions and we'll be taking them one by one. Meanwhile, there are certain video questions which have been asked by students of Kalam Labs from all across India. So I'm going to present the screen, sir, and show you a few of them which are there. Yeah. So the first question is from Meghna Singhal. I'll share the screen to share the video.
Should I stop sharing?
Yeah, sir. That will be helpful. Yeah.
Okay.
Great. So I think it is there. 1 second. Yeah.
Hi.
Hello, sir. Can you please tell me how to become a space scientist? Because I really want to become a space scientist when I grow up, and I don't know how.
Well, this is something that you can definitely do. Just stay in school, go to college, and you can study physics or biology, almost any kind of science you like, and become a space scientist, or you can study engineering and become an aerospace engineer that builds spacecraft like this. So it's a completely realistic objective. You just need to stay in school and go to college.
So the crux is, sir, that we have to stay in school and study hard. Is it like? Okay, so all the people who are doing science OP, schools are the thing. If you want to go on such missions, join your hands with such amazing missions, schools are the main thing. Even Matthew sir is telling us that. Now there's another question, sir, by
Hi.
Amishi Taparia.
Good evening. I am Saranj. The James Webb Telescope is a very strong telescope. So my question is, using that, will it be possible to closely observe stars of other galaxies as well?
To observe what? I'm sorry.
To observe stars of other galaxies.
Well,
yeah.
Only in the very closest other galaxies, like the Magellanic Clouds, for example, can we see the individual stars. In most galaxies that we look at, we won't be able to see the individual stars. We'll be looking at the galaxies as a whole.
Okay. So if we so is there a scope of a new powerful telescope as well in the future, which can help us to see individual stars of the far off galaxies as well?
Well, after JWST, it's possible that we can build even bigger telescopes in space.
Okay.
But we probably won't. You know, JWST is about the biggest telescope that we could launch and unfold the way you saw.
Yeah.
Telescopes even bigger than that will be assembled in space by robots.
That's so cool. Great, sir. There's another question. Let's hear them out.
Namaste, sir. My name is Vardhan Pandey and I'm from Gurgaon, India. I wanted to ask you, what are you really excited to see in the James Webb Telescope first that you could not see in the Hubble Space Telescope?
Oh, well, there's a lot of things. I'm very excited to see the first galaxies, to understand how galaxies formed. And I'm very, very excited, and I think almost everyone is very excited with the prospect that we may be able to find evidence of life in exoplanets, planets that are orbiting stars other than our own. This is some of the most exciting stuff in all of science. And of course, I'll be thrilled to see it work. So it'll be an exciting time, and we don't have long to wait. The launch will be in October, and the science will begin about 6 months after launch.
Okay, sir. Here's another question by...
Hello, sir. My name is here. And sir, my question to you is, while making the James Webb Telescope, did you ever feel like giving up, and why?
I'm sorry, could you repeat that question?
Yeah, I'll just repeat it, sir. It's basically that while creating the James Webb Telescope, did you ever think to give up, and why?
Oh, well, there were many challenges in building the JWST. We had to invent a lot of technologies that didn't exist. And so, you know, we never felt like giving up. Some of the people that are paying for the JWST may have felt that it was getting too expensive, but everyone stuck together and we finished the job. And now we will be able, the exploration will begin very soon.
That's great.
I think the moral of that story is that when things are tough, you just have to stick with it and believe in yourself and believe in the objective. And more often than not, you'll get there.
Great. So all the people, if you're acing to do some difficult task like building, you're aiming to build the next JWTS or your own new telescope or something like that, then the thing is that you have to stick to the problems, right? Great. So now, sir, there's another question which is on the screen.
Namaste, sir. My name is Vedanshi Pandey, and my question is, sir, can children around the world view through the telescope that you are making online, like the Google satellite?
Okay, could you repeat that one as well?
Yeah, I'll just repeat it, sir.
Is, sir, can children around the world view through the telescope that you are making online, like the Google satellite?
I think, sir, the question is that we can see Google satellite taking pictures. We can see our home through Google satellites. So can JMW, like James Webb Telescope, will be accessible to the kids or all the people around the world through some web portal where we can see the images on our own as well?
Yeah, I don't think that that the telescope itself will be accessible to kids around the world. But there will, I'm sure that there will be data sets that are designed for use in the classroom where kids will be able to look at the JWST data and explore it and maybe do science projects with it.
Oh, that's great, sir. That's amazing. Next, we have one last question, video question, and then we'll take it from the chat itself, sir. Yep.
Good evening, sir. I have two questions for you. The first one is that how powerful is James Webb Telescope? And the second one is what is the main part of James Webb Telescope which give the most support from it? Can you tell, please? In today, I am waiting for you in the today live session.
Okay.
So, you're going to have to repeat that one as well. Okay.
Yeah. So he's just asking that what is the main part of the JWTS? Like which part can be called as the heart of the James Webb Telescope?
Well, the real heart of any telescope are the science instruments, because they are the pieces that really do the science. So those four instruments that I mentioned are the real heart of the telescope.
Okay. So we can take quickly questions from the chat itself. So many people have been waiting to ask you questions, and we'll be taking all of them like one by one. Not all of them, but at least some of them which are quite famous over here. Okay, sure. So one of the famous questions which is there by Anyata, that sir, can we see wormholes as well through this telescope and prove their existence?
Can we see what?
Wormholes.
Oh, wormholes. No, I don't believe we'll be able to observe wormholes. We can only observe things that emit infrared light.
Okay. So wormholes will not be visible. Okay, so what's your take on extraterrestrial life? Because this is one of the most famous questions. Do you believe in that we are not alone among the space and we have to discover it, or you believe that it might be possible that we are the only ones living on Earth?
Well, I think it's very unlikely that Earth has the only life in the universe, particularly that we know that all stars have planets. Many of them have conditions similar to the Earth. So it's just a question of time before we detect extraterrestrial life. In fact, it will definitely happen within the lifetime of this audience, for sure.
Great. Next question, which is coming up, here we go with that. So So which other mission of NASA? So Suchi Sharma is asking that which other mission of NASA, like you are excited about it very much, like which other mission apart from the JWTS is one of the next game-changing missions there?
Well, the one that comes after the JWST that we're building right now is called the Roman Space Telescope. And it's designed to study something called dark energy. Remember, we talked about the universe is expanding. It turns out that the rate at which it's expanding is actually speeding up. And we don't know why. It's due to something called dark energy that we don't understand. And so the Roman Space Telescope, which will launch after JWST, is designed specifically to help us understand dark energy and what the fate of the universe will be.
Great, great, sir. So now I think so we can quickly have a ride on the Kalam Labs virtual simulator about the planets, because there are some individual questions there as with the planets as well. So I'll be sharing the screen, and so guys, so this is the virtual simulator of Kalam Labs. Many of the students, they basically use it and they explore space, cosmos, and everything through it. So let's one by one discover each and every planet which is there and talk about the impact that it will cause when we'll have the James Webb Telescope up and running in the space. So we can see Mars in front of us across the asteroid belt. So what's your take on Mars? Like, what do you think we can find there which can be groundbreaking or amazing in the next century?
Well, Mars is, is closest to the Earth, and Mars is the closest into the sun planet that JWST can observe. And of course, Mars, as you all know, is a place that we can actually travel to and study by direct exploration. We just very recently landed a robotic explorer on Mars to study its geology and also to study, to look for life, fossilized life on Mars. We believe Mars had an atmosphere just like Earth in the past. We believe it, we know that it had water on its surface as Earth does in the past. And we may be able to find evidence of fossil evidence of life on Mars and even microbial life on Mars. So that's what we're exploring for right now with the Perseverance rover that is working on Mars. And in just a few days, we will be flying a helicopter on Mars.
Yeah.
Now, JWST can see the whole planet. And so JWST might be able to support that direct exploration by monitoring dust storms and so forth occurring on Mars.
Great. So this is what the red planet has to do, has in the back from the JWTS. Next, we'll move to the giant which is present in our solar system, and we call it Jupiter. So, sir, you were talking about the Great Red Spot, and you said that with the JWTS, we can basically understand that why it is red and other interesting things about it. So what are the other parts of Mars, including the Great Red Spot, which are a mystery as of now, and with the James Webb Telescope, they could be solved in some time?
Well, with Jupiter, most of these planets, these outer planets, we've only been able to study by spacecraft that fly past them. And so we can only study them for a short time. But with JWST, we'll be able to observe them for a very, very long time and in the infrared part of the spectrum. So we can study different layers in the atmosphere of Jupiter. Jupiter is a big ball of gas, and we'll be able to study the Great Red Spot. Maybe we'll figure out why it's red. And we will likely discover new moons of Jupiter and Saturn. I think Jupiter has something like 73 moons that are known, and there will probably be more known after JWST observes it for a while.
Great, great, sir. So, new moons. So, as of now, is Hubble not able to see the moons of Jupiter and Saturn? And why so? Why it's difficult for satellites? Because they're quite closer in comparison to the far off things like which Hubble Space Telescope is seeing right now. So, why
Yeah.
is so, sir?
Hubble
Yeah.
can observe the planets, but Hubble observes in the ultraviolet invisible part of the spectrum.
Okay.
So cold objects would emit primarily in the infrared. And so JWST will be able to see things that Hubble cannot see. And JWST will be able to look deep into these planets to understand the vertical structure, if you will, of these big balls of gas, which are Jupiter and the outer planets.
Great, sir. Now we have reached the favorite. When we did a survey in the Kalam Labs community, that what is a favorite planet, sir? Then like 80% of them, everybody was talking about Saturn, the rings of Saturn, and why Saturn is so beautiful, and every other stuff like that. So, what's your take on Saturn? How do you look it as a planet and the future possibilities which it is hiding?
Well, one of the most striking features of Saturn are the rings. And the rings are the result of material being shepherded by gravity of lots and lots of moons of Saturn, many of which we really haven't discovered yet. And by searching for additional moons of Saturn that, say, the Cassini spacecraft was not able to see, we'll be able to understand the structure of the rings. That's one aspect that JWST will try and do.
Great, great, sir. So I think because of the time constraint which we have, it's already 7:10 around in India. So thanks a lot, sir, for coming into the session. And all the people who are there in the session, they're still posting questions. So I'll try to answer them like once the sessions are over, and I'll also forward it to you if there's something which is quite interesting and
Sure.
should be answered. So thanks a lot, sir, for coming into the session, and we are really grateful to know about these amazing things about the James Webb Telescope and other stuff.
My pleasure. Thank you for having me.
Thanks a lot, sir.
Bye-bye.
Bye, sir. So, hello, everyone. We just logged off with Matthew, sir, on the live stream, but that does not mean the show is still over. Because I have to tell you that what's coming up in the next week. The next week is also containing some amazing surprises, and we also have another guest coming up. Do you want to know him? Let's directly meet the next guest, which is coming the next weekend, and he's also from NASA itself. Okay, so now I'm going to introduce you to the next guest on the next Sunday, which is going to come after 6 days. Yani, like when sun will revolve 6 times, are like on its own axis, then we'll meet him. Okay, so now the time has come to basically introduce you to our next speaker, Mr. Jared, who is going to come here, and there's another surprise for all of you, okay, which is packed in the session itself. Okay, so now let's welcome the new guest. There's a video message which I want to show it to you from Mr. Jared, Dr. Jared, who's working as an aerospace engineer at NASA Institute of Glenn Research Center.
Hi, my name is Jared Wilhite, and I'm an aerospace engineer at the NASA Glenn Research Center. Next week, I'll be talking with all of you about all of the planets in our solar system. So tune in next week and check it out at the Kalam Labs YouTube Live Science Show next Sunday at 6 p.m. Can't wait to answer all of your questions. See you next week.
Whoa! So another scientist is coming at Kalam Labs at 6 p.m. next Sunday, and you have to come here because you are the curious people, right? So now I'm going to give out to you the Zoom link. I think Zoom link is not very important because there are so many people which are there, but I have to tell you some important things. Kalam Labs is basically the family of most curious and inquisitive and jigyasu people. The game which you were seeing right now, that's Kalam Labs Game Simulator, which is being used by all the kids who are enrolling at Kalam Labs. So if you want, then you can also join Kalam Labs by the link given in description. Apart from it, every curious thing about science, space, cosmos, black holes, alien life, whatever comes in your head, this is the place where we come. We take popular science concepts and look at it with a scientific angle. We do not believe in Jadoo, but we do believe in extraterrestrial life. Okay, so we do believe that bacteria can be found in outer space and aliens might be there, but we do not believe in some kind of other things, right? So with that, guys, all the people, all the Jigyasu people, there is one more tradition of Kalam Labs. Before ending any session, we all say and shout, "We love science." Okay, so now all the people present in the chat, the time has come when we have to show our true curiosity. And at Kalam Labs, this is the only non-scientific thing which we ever do. Okay, we talk about James Webb JWTS. We are going to meet Jared the next week at 6 p.m. We are inviting more ISRO scientists as well in the upcoming weeks. But the important thing here is that we are very curious about science. And in all of the things, one thing which we always do is that we shout, "We love science" with all our energy and jest. Okay, tomorrow at 6 p.m. we'll do another live stream in which I'll be taking whatever questions were there regarding the James Webb Telescope, and you can join in through the Zoom session. If you have not subscribed to the channel yet, please subscribe now because it's high time. Next week only, Jared is coming and joining us from Los Angeles, and all the people who are in the registered program section, I hope you are enjoying the session so far, and you can download the game and play it as much you like. Okay, with that, I'm going to begin the countdown timer. If you want to become a member of Kalam Labs and want to get the game which I was showing you, which is having lots and lots of missions, and it has been created by one of the best people in the country and across the world as well, then you can go to the link in description, www.kalamlabs.in/join. Okay, and now let's hold and behold and promise to come in tomorrow's live stream and the live streams which happen on Kalam Labs on a regular basis, as well as the live stream which is going to come at 6 p.m. next Sunday with Jared. Okay, so Jared OP in the chat. Everyone, they collect whatever questions you have and then post it on the comment sections of whatever videos you get, and you can basically go there. At every morning, we also post a daily question which you can answer and get a daily book, signed Stephen Hawking book as a prize money, as a prize award as well. Okay, so guys, now the time has come when we are going to wrap up the session. If you want to join Kalam Labs, the link is in description. My name is Harshit Awasthi. I'm one of the members at Kalam Labs, and I come and talk to you people, all the Jigyasus, curious, inquisitive, question mark people. Okay, all the people who want to know about how things work, why things work, and how we can become ISRO, NASA, or whatever, SpaceX, Tesla, Elon Musk, whatever you have in mind, because this is the place of the most curious people and kids. Okay, so now let's begin the tradition of Kalam Labs. At the count of 10, I'll basically ask you to type in "We love science" in the chat and like the video, because that is the tradition at Kalam Labs. Okay, so everyone, set down your key, like whatever keypad, or you're sitting on a laptop or whatever thing you are using, and type in "We love science" when I say 1. Okay, and you can also count with me. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We love science. And with that, we love science in the chat. Great. We love science OP. We love science OP. Like the video, share with your friends, and come next week. Come in the morning, come in the evening, whenever you have free time. Come to this place, because this is the place of the most curious and the coolest people you will ever find in the country. Okay, with that, we love science, we love science, we love science. If you have any questions for Matthew sir and it has not been answered, you can go to the YouTube comment and please ask a question. We will definitely answer them. And if there's something which we need to forward to Matthew sir directly, we will also do it. Okay. So guys, come on, and do attend the next session as well, because that only then you will be eligible for the certificate if you're entering Kalam Labs for the first time. Okay. Bye, OP in the chat. Take care of yourself. Be safe from the corona, and look up in the sky in the night and see some stars, and do tell your friends about them as well. Okay. Bye. We love science, and I'm curious.